Welcome to This Explainer. You know, when you first step into the world of secondary science, it's really easy to think it's just about memorizing this giant, intimidating encyclopedia of facts and equations, but I'm here to tell you it is so much more exciting than that. Secondary science is actually an empowering toolkit for exploring a highly complex world. It's a fundamental shift. We're moving from simply wondering, wow, look at that, to actively asking, wait, how do we know that? And how does it actually work? Today, we're going to unpack that toolkit together and show you exactly how to use it.
Think of it like being an explorer. You really have two essential conceptual tools in your kit, a magnifying glass and a compass. The magnifying glass symbolizes careful observation, right? It's about noticing patterns, looking incredibly closely, and paying attention to those tiny details you'd normally just walk right past. But observation alone just isn't enough. That's why we have the compass. The compass reminds us that exploration needs purposeful direction. It's about asking the right questions, choosing the appropriate models, and knowing the exact limits of where our ideas apply. Together, they show us that scientific exploration isn't just wandering around aimlessly. It's about making sense of our world with absolute care and purpose.
So here's our exact game plan for today. We'll start with the Explorer's Toolkit, then move to the power of simplification. After that, we'll talk about science as a universal language, unpack laws, theories, and predictions, practice the art of estimation, and finally, look at breaking the boundaries of scientific subjects. All right, let's jump right into part one, the Explorer's Toolkit, moving beyond observation.
And that leads us directly into part two, the power of simplification, building models. You see, the natural world is wonderfully messy and complex, but studying it in full detail all at once? That's basically impossible. So, how do scientists actually cope? Well, they build models. And the absolute key word here is deliberately. Models deliberately ignore certain details to focus only on what's most important. When a physicist studies a falling object, for example, they might completely ignore air resistance just to understand the pure, isolated effect of gravity. Or, when a biologist studies how a heart pumps blood, they might ignore the individual cells to understand the organ as a whole system. Ignoring these things isn't a mistake. It's a brilliant, purposeful choice to keep things simple enough to actually find the answers we're looking for.
Let's apply this to something practical. Imagine you're trying to hit a cricket ball for a 6, and you want to build a simple model to see if it'll actually cross the boundary. What are the genuinely important details here? Well, it's the mass of the ball, its speed, and the direction it's hit. Now, what details do we deliberately ignore? The brand of the bat, the exact color of the ball, or how much grass happens to be on the field? Stripping away all that unnecessary noise is what allows us to focus entirely on the core physics of the problem.
There's this fantastic quote, "Science often begins by ignoring details," and history backs this up perfectly. When the famous physicist Meghnad Saha studied the light coming from distant stars, he didn't try to model every single atom, every reaction, or every tiny movement inside that star. That would be completely impossible. Instead, he kept it brilliantly simple. He just treated the star as a hot gas. By literally ignoring millions of complex processes, he successfully figured out how the color of a star is deeply connected to its temperature. That is the true power of simplification right there.
Which brings us to part three, a universal language, precision and math.
So a crucial thing to understand is that science uses language in an incredibly precise way. Think about it. We casually toss around words like work, force, cell, or reaction in our everyday conversations all the time. But in science, those words carry highly specific, clear, and absolutely unambiguous meanings. This shared language, along with standardized symbols and math, is what allows scientists across the entire globe to communicate, compare their results, and build ideas together without any confusion.
To show you exactly what happens when we don't use a shared, unambiguous language, let me share a pretty shocking story. 15,000. That is the exact number of liters of fuel a passenger aircraft was short while flying mid-air. Why? Simply because of a mix-up in units. The ground crew calculated the fuel needed using pounds per liter instead of kilograms per liter. So using standard, agreed-upon units isn't just about trying to pass a science test. It is literally a matter of keeping airplanes safely in the sky.
And hey, it's not just for high-tech aviation either. Think about the person selling vegetables down the street using a simple pan balance. When we buy vegetables, we absolutely expect a kilogram to mean the exact same amount everywhere we go. Imagine the total chaos if every single person used a completely different weight. Standard units ensure that global science can be compared accurately. Yes, but they also ensure basic fairness and trust in our daily lives and trade.
All right, part 4, laws, theories, and predictions, frameworks of science.
As scientists measure and observe all these things, they build frameworks to organize their understanding. The first term you're going to encounter a lot is a law. Now, a law is simply a description of a regular pattern we repeatedly observe in nature. For instance, when you're standing on a bus and it suddenly hits the brakes, you naturally jerk forward. Newton's laws of motion beautifully describe that reliable pattern. Simply put, a law tells us what happens.
Now, we really need to clear up a massive misconception. In everyday language, people constantly say, "Oh, I have a theory about that," meaning they just have a wild guess. But in science, a theory is absolutely not just a guess. A scientific theory is a deeply tested explanation of why those specific patterns occur, and it's based on absolute mountains of evidence. The atomic theory, for example, explains how molecules are actually formed. It's an explanation born from rigorous testing, not just a random hunch.
And then we have principles. You can think of a principle as a broad, guiding idea that we can apply to help us make sense of tons of different situations. A perfect example of this is the conservation of energy. You can apply this one broad principle to understand what's happening whether you're burning a piece of coal for heat or just calculating the energy it takes your body to climb up a set of stairs.
Now, these frameworks naturally allow scientists to make predictions, but here's the really cool part. What happens when those predictions turn out to be wrong? Well, when predictions do not match observations, it's actually not a weakness of science, it is its greatest strength. This is the ultimate fail-forward mindset. When a prediction fails, scientists don't just reject ideas based on opinion. They re-examine their evidence. Science is always open to being corrected by nature itself. And honestly, that willingness to adapt based on new evidence is exactly what makes science so incredibly reliable.
Moving to part 5, the art of estimation, building intuition.
I'll be honest, this is one of my absolute favorite tools in the entire kit. In science, careful reasoning actually matters a whole lot more than getting a perfectly precise calculation right out of the gate. Sometimes you just need an estimate to see if an answer is even reasonable. To do this, we follow 3 steps. First, understand the situation. Second, identify the important quantities. And third, make a rough estimate. For example, is 100 grams of rice enough to feed a family of 4 for an entire month? Well, if you know a typical adult needs about 2,000 calories a day, you definitely don't need a calculator to know that 100 grams for a month is clearly impossible, while buying a few tons would be way too much. Estimation is what builds your scientific intuition.
Let's actually try one together right now that leads to an astonishing number, 10,000. That is roughly the number of liters of air you breathe in every single day. Sounds crazy, right? But how do we estimate that without some fancy lab equipment? Well, we know a person takes about 20,000 breaths a day. Now, if you picture a typical rubber party balloon, which holds about 2 liters of air, it takes roughly 4 or 5 normal breaths to blow it up. That means one breath is roughly half a liter. So 20,000 breaths times half a liter gives us exactly 10,000 liters of air a day. You just reason that out entirely with simple estimation. Pretty cool, right?
Finally, let's hit part 6, breaking the boundaries, interdisciplinary science.
In school, we tend to put science into neat little boxes. Physics here, chemistry there, biology over there. But guess what? Nature completely ignores those boundaries. Take a standard surgical mask, an everyday object we all got very used to during the COVID-19 pandemic. To make a mask that actually protects us, we can't just rely on one single subject.
This object brilliantly illustrates how everything connects. Just think about what it takes to actually make that mask work. You need physics to understand the particle motion and the static electricity that traps the dust. You need chemistry to understand the specific properties of the polymer fibers the mask is made of. You need biology to know the actual size and behavior of the virus itself. And you need mathematics to model the airflow and filtration efficiency. A single, simple mask seamlessly weaves together all of these disciplines to solve a very real-world problem.
So, to wrap up this explainer, I want to leave you with a bit of a challenge. You see wild claims online all the time, right? Stuff like, eating food during a solar eclipse is harmful. Now that you have your Explorer's Toolkit packed and ready, how do you tackle this? Well, you start asking measurable questions. An eclipse is basically just a shadow. Does the temperature drop significantly? Does food normally spoil if you just leave it in a shadow for a few minutes? Of course not. There is literally no physical, chemical, or biological mechanism to support that claim. Science isn't just something you read in a textbook. It's an active way of thinking critically about the entire world around you. So the real question is, how are you going to use your new toolkit today? Thanks so much for exploring with me, and I'll see you in the next explainer.